YAML. Torch. Trunc. Description. The torch, trunc function returns a new tensor with the truncated value of each element in the input tensor. Truncation means that the fractional part of each element is discarded, and the integer part is returned. Inputs. Input a tensor containing the elements to be truncated. Outputs. Output a tensor with the same size and data type as the input tensor, containing the truncated values of each element. Steps. The function iterates through each element in the input tensor. For each element, it calculates the truncated value by discarding the fractional part and keeping the integer part. The truncated value is then stored in the corresponding position in the output tensor. Challenges and fixes. Challenge 1 input tensor is not a valid tensor. Sample use case that resulted in challenge 1. The input tensor is a string or a list instead of a tensor. Fixes to challenge 1: convert the input to a valid tensor using the torch tensor function. Challenge 2: input tensor has elements that are not numbers. Sample use case that resulted in challenge 2: the input tensor contains strings or other non-numeric elements. Fixes to challenge 2: ensure that all elements in the input tensor are numeric before applying a torch trunc function. Torch float power. Description. The torch float power function calculates the element-wise power of a tensor with another tensor or a scalar. This operation is equivalent to raising each element of the first tensor to the power specified by the corresponding element in the second tensor or by the scalar. Inputs. Input 1: a p-torch tensor, representing the base for the power operation. Input 2: another p-torch tensor of the same size as the first tensor, or a scalar. This input defines the exponents for each element in the base tensor. Outputs. Output 1: a p-torch tensor of the same size as the input tensors, containing the element-wise results of the power operation. Steps. Step 1: for each element in the input tensor, the function accesses the corresponding exponent from the second input or the scalar value. Step 2: the element of the input tensor is then raised to the power specified by the exponent, and the result is stored in the output tensor at the corresponding position. Challenges and fixes. Challenge 1: division by 0. Sample use case that resulted in challenge 1: when the base is 0 and the exponent is negative, the operation results in division by 0, leading to an error. Fixes to challenge 1: to prevent division by 0. You can use a conditional statement or a try-except block to handle these cases. For example, you can set the result to a specific value such as infinity or raise a custom exception. Challenge 2: overflow. Sample use case that resulted in challenge 2: when dealing with large exponents or large base values, the calculation may result in an overflow, leading to an inaccurate or infinite result. Fixes to challenge 2: to handle overflow. You can use appropriate data types with larger ranges, e.g., torch, float 64 for larger numbers, or use logarithmic techniques to reduce the magnitude of the calculations. Torch flow. Description. The torch flow function returns a new tensor with the flow of each element in the input tensor. The floor of a number is the greatest integer less than or equal to that number. Inputs. Input a tensor of any supported data type. Outputs. Output a tensor of the same shape and data type as the input tensor, containing the flow of each element in the input tensor. Steps. The function iterates over each element in the input tensor. For each element, it calculates the flow using the flow function from the underlying numerical library, e.g., NumPy, QBLAS. The result is stored in a new tensor. which is then returned as the output. Challenges and fixes. Challenge 1 data type issues. The flow function only works with numerical data types. If the input tensor contains non-numerical data, e.g., strings, it will raise an error. Sample use case that resulted in challenge 1. Torch, floor torch, tensor hello, world. Fixes to challenge 1. Convert the input tensor to a numerical data type before applying the flow function. For example, torch, floor torch, tensor 1.5. 2.8.float. Challenge 2 negative values. The flow function returns the greatest integer less than or equal to the input value. For negative numbers, this means that the flow will be a smaller negative number. Sample use case that resulted in challenge 2. Torch, floor torch, tensor -1.5, -2.8. Fixes to challenge 2. Be aware that the result of flow for negative numbers will be a smaller negative number. Torch, floor torch, tensor -1.5, -2.8 will return torch, tensor 2, -3. Torch flow divide. Description. This function performs flow division element-wise between two tensors. It returns the largest integer smaller than or equal to the division result. Input 1. The dividend tensor. This can be a scalar, A1D tensor, A2D tensor, or a tensor of higher dimensions. Input 2. The divisor tensor. This can be a scalar, A1D tensor, A2D tensor, or a tensor of higher dimensions. Output 1. The resulting tensor after flow division. The shape of the output tensor will be the same as the shape of the input tensor with the larger number of dimensions. If the input tensors have different shapes, broadcasting will be applied. Step 1. Divide each element of the dividend tensor by the corresponding element of the divisor tensor. Step 2. For each result, find the largest integer that is smaller than or equal to the result. This is the flow division operation. Challenge 1. Division by 0. Dividing any number by 0 results in an undefined value. Sample use case that resulted in challenge 1. Python. Import torch. A torch, tensor 1. 2. 3. B torch, tensor 0. 2. 0. Torch, flow divider, B. Fixes to challenge 1. Avoid dividing by 0. Check for 0 values in the divisor tensor and handle them appropriately. For example, you can replace 0 values with a small number close to 0. Or you can use a conditional statement to skip the division operation for 0 values. Challenge 2. Input tensors with different shapes. The flow division operation requires that the input tensors have compatible shapes. If the shapes are not compatible, broadcasting will be applied. Sample use case that resulted in challenge 2. Python. Import torch. A torch, tensor 1. 2. 3. 4. B torch, tensor 2. 3. Torch, flow divider, B. Fixes to challenge 2. Ensure that the input tensors have compatible shapes. If the shapes are not compatible, you can either reshape the tensors or use broadcasting. Broadcasting will automatically expand the smaller tensor to match the shape of the larger tensor. Torch, fmod. Description. The torch, fmod function computes the element-wise remainder of division. In other words, it returns the remainder when the first input tensor is divided by the second input tensor. Inputs. Input 1. Input, a tensor containing the numbers to be divided. Input 2. Other, a tensor containing the divisors. Outputs. Output 1. Result, a tensor containing the element-wise remainders. Steps. Step 1. For each element in input, The function performs a division by the corresponding element in other. Step 2. The remainder of this division is then stored in the result tensor. Challenges and fixes. Challenge 1. Division by 0 if any element in other is 0. The corresponding element in result will be none, not a number. Sample use case that resulted in challenge 1. Torch f mod torch tensor 1, 2, 3 torch tensor 0, 1, 0. Fixes to challenge 1 to handle division by 0. You can use a conditional statement to check for 0 values in other and assign a default value to the corresponding elements in result. For example, Python result torch, where other 0 torch f mode input other torch tensor 0. Challenge 2 input tensors with different shapes if input and other have different shapes. The torch fmod function will broadcast the tensors to match their shapes before performing a division. This can sometimes lead to unexpected results if the broadcasting behavior is not fully understood. Sample use case that resulted in challenge 2 torch fmod torch tensor 1, 2, 3 torch tensor 1. Fixes to challenge 2 to avoid unexpected broadcasting behavior. Ensure that input and other have compatible shapes. If necessary, use functions like torch, reshape or torch, and squeeze to adjust the shapes of the tensors before applying torch fmod. YAML torch frac. Description. The torch frac function in ptorch calculates the fractional part of each element in a tensor. It essentially takes the input tensor and returns a new tensor where each element is the decimal portion of the corresponding element in the input tensor. Inputs. Input 1. A ptorch tensor. This tensor can be of any supported data type, e.g. float, double, etc. It can be a scalar, vector, matrix, or any higher order tensor. Outputs. Output 1. A ptorch tensor with the same shape and data type as the input tensor. This output tensor contains the fractional part of each element from the input tensor. Steps. Step 1. For each element in the input tensor, the torch frac function determines the whole number part integer part. Step 2. It then subtracts the whole number part from the original element, leaving only the fractional part. Challenges and fixes. Challenge 1. Input tensor with negative values. Sample use case that resulted in challenge 1 when the input tensor has negative values. The torch frac function still returns the fractional part, but the result might not be the expected one based on the definition of the fractional part for negative numbers. Fixes to challenge 1. Ensure that you understand how torch frac handles negative numbers. If you need the fractional part of a negative number, you might need to apply a different calculation. Challenge 2. Input tensor with integer data type. Sample use case that resulted in challenge 2 if the input tensor contains integer values, e.g. torch.int, torch, long. The fractional part of all elements will be 0. Fixes to challenge 2. Convert the integer tensor to a floating point data type, e.g. torch, float, torch, double before applying torch frac if you intend to extract the fractional part. Torch frexup. Description. The torch frexup function decomposes a tensor into its mantissor and exponent components. It essentially separates the floating point number into its significant digits mantissor and its power of 2 exponent. This is useful for representing numbers in a normalized form, especially when working with very large or very small values. Inputs. Input 1. The input tensor containing the floating point numbers. Outputs. Output 1, a tensor containing the mantensor components of the input tensor. The mantensor values will be in the range 0.5. 1 exclusive of 1. Output 2, a tensor containing the exponent components of the input tensor. The exponents are integers representing the power of 2 that multiplies the mantensor to obtain the original number. Steps. Step 1, the torch Freksup function takes a tensor as input and performs the following operations for each element in the tensor. It determines the sign, exponent, and mantensor of the floating point number. It isolates the mantensor component, ensuring it falls within the range 0.5. 1 by shifting the binary representation if needed. It extracts the exponent component as an integer representing the power of 2. Step 2, it returns two tensors. One containing the mantensor values and the other containing the exponent values. Both of the same shape as the input tensor. Challenges and fixes. Challenge 1, input tensor containing 0 or none values. Sample use case when the input tensor contains 0 or none not a number values. The torch Freksup function may produce unexpected results. Fixes. Ensure that the input tensor contains valid floating point numbers before calling torch Freksup. If necessary, handle 0 and none values separately by replacing them with appropriate values or filtering them out. Challenge 2, dealing with extremely small or large numbers. Sample use case when dealing with extremely small or large numbers. The exponent component may become very large or very small, potentially exceeding the limits of integer data types. Fixes. Use a suitable data type for the exponent tensor, e.g. torch long to accommodate larger exponent values. Consider employing numerical stability techniques, e.g. logarithmic operations if the exponent values become excessively large or small and affect subsequent calculations. Torch gradient. Description. The torch gradient function computes the gradient of a multidimensional tensor along specified dimensions. It uses finite differences to approximate the derivative at each point. Inputs. Input 1, input, a multidimensional tensor representing the function whose gradient needs to be calculated. Input 2, dim optional, a list of integers indicating the dimensions along which to compute the gradient. If not specified, the gradient is calculated along all dimensions. Outputs. Output 1, a list of tensors, where each tensor corresponds to the gradient along a specified dimension. The shape of each output tensor is the same as the input tensor, with an additional dimension added at the end to represent the gradient. Steps. Step 1, the function iterates through each dimension specified in dim or all dimensions if dim is not provided. Step 2, for each dimension, it calculates the gradient using finite differences. This involves subtracting adjacent elements along that dimension and dividing by the spacing between them. Challenges and fixes. Challenge 1, incorrect dimension specification. Providing an incorrect dimension index in the dim argument can lead to an error. Sample use case that resulted in challenge 1, torch gradient tensor DIM1, 2, 3, where the tensor has only 2 dimensions. Fixes to challenge 1: ensure the dim list contains valid dimension indices within the range of the input tensor's dimensions. Challenge 2: boundary handling. The gradient calculation near the boundaries of the input tensor might be inaccurate due to the finite difference approximation. Sample use case that resulted in challenge 2, torch gradient tensor, where the tensor has a small number of elements along certain dimensions. Fixes to challenge 2: consider using boundary conditions. such as zero padding or periodic boundary conditions, to improve the accuracy of the gradient calculation near the boundaries. Torch, LDEXP. Description: the torch, LDEXP function calculates the result of multiplying a floating point number by 2 raised to the power of an integer exponent. Inputs: x, a tensor containing the floating point numbers to be multiplied. Exponent, an integer tensor representing the exponents to which 2 will be raised. It must have the same shape as x or be a scalar. Outputs: y, a tensor of the same shape as x containing the results of the calculation x2 exponent. Steps: for each element in x and exponent, the function calculates x2 exponent. The result is returned as a tensor of the same shape as x. Challenges and fixes. Challenge 1: input tensors must have the same shape or exponent must be a scalar. Sample use case: torch, LDEXPTORCH, tensor 1.0. 2.0. Torch, tensor 1. 2. 3. Fixes: ensure that x and exponent have the same shape, or exponent is a scalar. Challenge 2: exponent must be an integer tensor. Sample use case: torch, LDEXPTORCH, tensor 1.0. 2.0. Torch, tensor 1.5. 2.5. Fixes: ensure that exponent is an integer tensor. You can use torch, round or torch, flow to round the values in exponent to the nearest integer. Torch, lerp. Description: the torch, lerp function in PTorch performs linear interpolation between 2 tensors. It takes 2 tensors start and end and a weight as input and calculates the interpolated values along the straight line between the start and end tensors. Inputs: start, the starting tensor for interpolation. It can be of any shape and data type, but it must have the same shape as the end tensor. End, the ending tensor for interpolation. It must have the same shape and data type as the start tensor. Weight, a tensor or a scalar value representing the interpolation weight. It determines the position on the line between the start and end tensors. A weight of 0.0 returns the start tensor. A weight of 1.0 returns the end tensor. And weights between 0.0 and 1.0 return interpolated values between the start and end tensors. Outputs: output, a tensor containing the interpolated values. The output tensor has the same shape and data type as the start and end tensors. Steps: the function first checks if the input tensors are of the same shape and data type. If they are not, an error is raised. Then, the function calculates the weighted average of the start and end tensors based on the weight parameter. The formula used for the calculation is output start weight end start. Challenges and fixes. Challenge 1: the input tensors do not have the same shape or data type. Sample use case: if the start tensor is a 1/2 tensor and the end tensor is a 2/1 tensor, an error will be raised. Fixes: ensure that the input tensors have the same shape and data type. You can use the torch, reshape function to change the shape of a tensor if necessary. You can use the torch.to function to convert the data type of a tensor if necessary. Challenge 2: the weight parameter is outside the range of 0.0 to 1.0. Sample use case: if the weight parameter is set to 2.0, the output tensor will contain values that are outside the range of the start and end tensors. Fixes: ensure that the weight parameter is within the range of 0.0 to 1.0. If the weight parameter is outside this range, the output tensor will contain extrapolated values, which may not be desirable. YAML. Torch, L gamma. Description computes the logarithm of the gamma function. The gamma function is a generalization of the factorial function to complex numbers. Inputs. Input a tensor of real numbers. The elements of the tensor must be greater than 0. Outputs. Output a tensor of the same size as input, containing the logarithm of the gamma function of each element in input. Steps. The torch L gamma function calculates the natural logarithm of the gamma function of each element in the input tensor. The gamma function is defined as the integral from 0 to infinity of tx1 xpt dt. Challenges and fixes. Challenge 1 input contains negative or 0 values. Sample use case that resulted in challenge 1. Torch L gamma torch tensor -1, 0, 1. Fixes to challenge 1. Ensure the input tensor contains only positive numbers. Challenge 2 input is not a tensor. Sample use case that resulted in challenge 2. Torch L gamma 1. Fixes to challenge 2. Convert the input to a tensor using torch tensor. YAML. Torch.log. Description. The torch.log function calculates the natural logarithm of each element in a p-torch tensor. It is a fundamental mathematical operation used in various domains like machine learning, data analysis, and scientific computing. Inputs. Input a p-torch tensor representing the input values. Details. The input tensor can be of any shape and data type supported by p-torch. The function will compute the natural logarithm of each element in the tensor. Outputs. Output a p-torch tensor of the same shape as the input tensor. Details. The output tensor contains the natural logarithm of each corresponding element from K. Input tensor. Steps. Step 1. The torch.log function iterates through each element in the input tensor. Step 2. For each element, it calculates the natural logarithm using the mathematical function log, where x is the element's value. Step 3. The calculated logarithm values are stored in a new tensor of the same shape as the input tensor. Challenges and fixes. Challenge 1. Handling negative inputs. Sample use case that resulted in challenge 1 when the input tensor contains negative values. Torch.log will raise a runtime error because the natural logarithm is not defined for negative numbers. Fixes to challenge 1. Use the torch.log 1p function. This function calculates the natural logarithm of 1 the input tensor, which can handle negative inputs effectively. Manually handle negative inputs. Check for negative values in the input tensor and replace them with a small positive value before applying the torch.log function. Challenge 2. Handling 0 inputs. Sample use case that resulted in challenge 2 when the input tensor contains 0 values. Torch.log will return INF negative infinity as the logarithm of 0 is undefined. Fixes to challenge 2. Use the torch.log 1p function similar to handling negative inputs. This function can effectively handle 0 values as well. Manually handle 0 inputs. Replace 0 values in the input tensor with a small positive value before applying torch.log to avoid INF outputs. Torch.log 10. Description. Inputs. Input a tensor containing numerical values. Output a tensor containing the BASE10 logarithm of the input tensor. Steps. Step 1. The function calculates the BASE10 logarithm of each element in the input tensor. Step 2. The results are stored in a new tensor, which is returned as the output. Challenge 1. Input contains 0 and negative values. Sample use case that resulted in challenge 1 torch.log10 torch. Tensor 0. -1. 2. Fixes to challenge 1. The function will return INF for 0 values and none for negative values. This is because the logarithm is undefined for these values. Challenge 2 input contains values that are very close to 0 or very large. Sample use case that resulted in challenge 2 torch.log10 torch. Tensor 1e-10. 1e10. Fixes to challenge 2. The function may return inaccurate results for values that are extremely small or large. This is because of limitations in floating point arithmetic. To address this, you can consider using a different logarithmic function, such as torch.log or torch.log2, depending on your specific needs. Torch.log1p. Description. The torch.log1p function computes the natural logarithm of one input, element-wise. It's designed to handle values close to 0 more accurately than directly taking the logarithm. Inputs. Input a tensor containing numerical values for which you want to calculate the log1p. Outputs. Output a tensor of the same shape as the input, containing the natural logarithm of 1 each element of the input. Steps. Adds 1 to each element of the input tensor. Calculates the natural logarithm base A of the resulting elements. Challenges and fixes. Challenge 1 input contains negative values. Sample use case calculating log1p on a tensor containing -1. Fixes input must be greater than or equal to -1. This is because log1px is undefined for x -1. You can either clamp the input to -1 or use a different function if you need to handle negative values. Challenge 2 input contains very small values close to 0. Sample use case calculating log1p on a tensor containing 1e10. Fixes using log1p is generally preferred for values near 0 because it avoids numerical instability issues that might arise from directly calculating log1x when x is very small. Torch.log2. Description. This function computes the BASE2 logarithm of the input tensor element-wise. Inputs. Input a tensor of any shape containing the values to calculate the logarithm. Outputs. Output a tensor of the same shape as the input tensor, containing the element-wise BASE2 logarithms of the input. Steps. The function iterates through each element of the input tensor. For each element, it calculates the BASE2 logarithm using the math.log2 function. The calculated logarithm value is stored in the corresponding element of the output tensor. Challenges and fixes. Challenge 1 input contains negative or 0 values. Sample use case that resulted in challenge 1. Torch.log2 torch. Tensor -1. 0. 1. Fixes to challenge 1. The function raises a value error if any element in the input tensor is negative or 0. Challenge 2 input tensor contains non-floating point values. Sample use case that resulted in challenge 2. Torch.log2 torch. Tensor 1. 2. 3. D-type torch.int. Fixes to challenge 2. The function implicitly converts the input tensor to a floating point tensor before calculating the logarithm. Torch. Logadexup. Description. Calculates the logarithm of the sum of exponentials of the given inputs. This function is mathematically equivalent to log exp input 1 exp input 2. Inputs. Input 1 a tensor of any shape containing the first input. Input 2 a tensor of the same shape as input 1 containing the second input. Outputs. Output a tensor of the same shape as the input tensors containing the result of the Logadexup operation. Steps. The function first calculates the exponentials of both input tensors expinput1 and expinput2. It then sums the exponentials expinput1 expinput2. Finally, it calculates the logarithm of the sum log expinput1 expinput2. Challenges and fixes. Challenge 1: overflow. If the input values are very large, the exponentials can overflow, resulting in an infinite value. Sample use case that resulted in challenge 1: torch, logadec torch, tensor 1000. Torch, tensor 1000. Fixes to challenge 1: use the torch, logadexup function instead of calculating the exponentials manually. It handles overflow internally. Challenge 2: underflow. If the input values are very small, the exponentials can underflow, resulting in a zero value. Sample use case that resulted in challenge 2: torch, logadec torch, tensor 1000. Torch, tensor 1000. Fixes to challenge 2: use the torch, logadexup function instead of calculating the exponentials manually. It handles underflow internally. Torch logadexup 2. Description. Calculates the log of the sum of exponentials of the given inputs in base 2. This function is mathematically equivalent to log2 exp2 input 1 express 2 input 2. Inputs. Input 1: a tensor of any shape. It represents the first input to the logadexup 2 operation. Input 2: a tensor of the same shape as input 1. It represents the second input to the logadexup 2 operation. Outputs. Output: a tensor of the same shape as input 1 and input 2. It contains the result of the logadexup 2 operation, which is the log base 2 of the sum of exponentials of the two input tensors. Steps. The function calculates the exponentials of both input tensors in base 2 express 2 input 1 and express 2 input 2. It then sums the two exponential results. Finally, it computes the logarithm base 2 of the sum. Challenges and fixes. Challenge 1: numerical instability. When the input values are very large or very small, the calculation of exponentials can lead to overflow or underflow errors. Sample use case that resulted in challenge 1: when input 1 and input 2 are large positive numbers, express 2 input 1 and express 2 input 2 can become extremely large, causing an overflow error. Fixes to challenge 1: the function handles numerical instability by internally using the logsumexup technique. This technique avoids direct calculation of exponentials by working with logarithms directly. Challenge 2: input tensor shapes. The function requires that both input tensors have the same shape. Sample use case that resulted in challenge 2: when input 1 is a 2/3 tensor and input 2 is a 3/2 tensor. The function will throw an error because the input shapes are not compatible. Fixes to challenge 2 ensure that the input tensors have the same shape before calling the function. If necessary, use broadcasting or reshaping operations to make the shapes compatible. Torch, logical in. Description performs element-wise logical and operation on two tensors. The logical and operation returns true if both inputs are true. Otherwise false. Inputs. Input 1: a tensor of arbitrary shape. The data type should be Boolean. Input 2: a tensor of the same shape as input 1. The data type should be Boolean. Outputs. Output 1: a tensor of the same shape as input 1 and input 2, containing the result of the logical and operation. The data type is Boolean. Steps. Step 1: the function iterates over each element in the input 1 and input 2 tensors. Step 2: for each corresponding pair of elements in input 1 and input 2, it performs the logical and operation. If both elements are true, the output element is set to true. Otherwise, it is set to false. Challenges and fixes. Challenge 1 input tensors have different shapes. Sample use case that resulted in challenge 1 applying torch, logical and on 2 tensors with different dimensions. Fixes to challenge 1 use broadcasting to ensure that the input tensors have the same shape before applying torch, logical in. This can be achieved by either reshaping one of the tensors or using the broadcast tensors function. Challenge 2 input tensors have incompatible data types. Sample use case that resulted in challenge 2 trying to apply torch, logical and on tensors with data types other than Boolean. Fixes to challenge 2 convert the input tensors to Boolean data type before applying torch, logical and using the to method. Torch, logical not. Description. The torch, logical not function performs the logical not operation on a tensor. Element-wise, it inverts the truth value of each element in the input tensor. Inputs. Input 1 input, a tensor of any supported data type. It represents the input for the logical not operation. Outputs. Output 1 out, a tensor of the same shape and data type as the input tensor. It contains the result of the logical not operation. Each element in out is the inverse of the corresponding element in the input tensor. Steps. Step 1 the function iterates through each element in the input tensor. Step 2 for each element. It performs the logical not operation. This means that if the element is true 1 or any non-zero value, the corresponding element in the output tensor becomes false 0. Conversely, if the element is false 0, the corresponding element in the output tensor becomes true 1. Challenges and fixes. Challenge 1 handling non-Boolean data types torch, logical not is designed to work with Boolean tensors. If you input a tensor with non-Boolean data types e.g. integers or floats, the function treats non-zero values as true and zero values as false. Sample use case that resulted in challenge 1 torch, logical not torch, tensor 1. 2, 0, minus 1 will return tensor 0, 0, 1, 0. Fixes to challenge 1 to ensure consistent behavior with Boolean values. It's best practice to convert the input tensor to a Boolean type using torch, bool or input, bool. Before applying torch, logical not. Challenge 2 handling tensors with non-standard data types. The function might not work as expected with custom data types that do not have a well-defined notion of truthiness, e.g. complex numbers. Sample use case that resulted in challenge 2 torch, logical not torch, tensor 11j. O1j might not produce the desired outcome. Fixes to challenge 2 in such cases. Consider converting the input tensor to a more appropriate data type before applying the logical not operation. You might need to define custom logic for determining truthiness based on your specific data type. Torch logical OR. Description explain in detail performs element-wise logical OR operation on 2 tensors. The operation returns a tensor with the same size as the input tensors. For each element in the output tensor, it contains a Boolean value indicating if either corresponding element in the input tensors is true. Input 1 explain in detail a tensor with Boolean values. Input 2 explain in detail a tensor with Boolean values. The tensor should have the same shape as input 1. Output 1 explain in detail a tensor containing Boolean values resulting from the logical OR operation. The shape of the output tensor is the same as the input tensors. Step 1 explain in detail the torch, logical OR function iterates through the corresponding elements. of the input tensors, performing logical OR operation on each pair of elements. Step 2. Explain in detail if either element in the pair is true. The corresponding element in the output tensor is set to true. Otherwise, it is set to false. Challenge 1. Explain in detail the input tensors should have the same shape. Sample use case that resulted in challenge 1 trying to perform logical OR on tensors of different shapes will result in an error. Fixes to challenge 1. Ensure that the input tensors have the same shape before applying torch. Logical OR. You can use functions like torch, reshape or torch, broadcast tensors to adjust the shapes of tensors if necessary. Challenge 2. Explain in detail the input tensors should have Boolean values. Sample use case that resulted in challenge 2 if the input tensors contain non-Boolean values. The torch, logical OR function might return unexpected results. Fixes to challenge 2. Convert the input tensors to Boolean type using functions like torch, bool or torch, tensor, d-type torch, bool before applying torch, logical OR. Torch, logical XOR. Description. Inputs. Input 1 the first input tensor. Input 2 the second input tensor. Must have the same shape as the first input tensor. Output 1 the result of the logical XOR operation between input 1 and input 2. The output tensor has the same shape as the input tensors. Steps. Step 1. The function compares each element of the input tensors and returns a tensor where each element is 1 if the corresponding elements of the input tensors are different. 1 is true and other is false, and 0 otherwise. Challenge 1. Input tensors with different shapes. Sample use case that resulted in challenge 1. Input 1 torch, tensor true, false, true. Input 2 torch, tensor true, false. Fixes to challenge 1. Ensure that the input tensors have the same shape. Use torch, broadcast tensors to automatically broadcast the input tensors to a compatible shape if they are not already. Challenge 2. Input tensors with different data types. Sample use case that resulted in challenge 2. Input 1 torch, tensor 1, 0, 1. Input 2 torch, tensor true, false, true. Fixes to challenge 2. Ensure that the input tensors have the same data type. Use torch, bool to convert the input tensors to Boolean data type if they are not already. Challenge 3. Input tensors with different devices. Sample use case that resulted in challenge 3. Input 1 torch, tensor true, false, true, tokuda. Input 2 torch, tensor true, false, true. Fixes to challenge 3. Ensure that the input tensors are on the same device. Use torch, device to move the input tensors to the same device if they are not already. Torch logit. Description. The torch, logit function in PTorch is used to calculate the logit of a given input tensor. The logit function, also known as the inverse sigmoid function, transforms a probability value typically between 0 and 1 into a log odds value, representing the logarithm of the ratio of the probability of the event occurring to the probability of the event not occurring. This function is commonly used in machine learning and deep learning for tasks like classification, where it helps convert probabilities into log odds values, which are often more suitable for optimization. Inputs. Input 1 input tensor. The input tensor containing probability values. This tensor can be of any shape, but the values must be in the range 0, 1. Input 2 apes float. Optional, a small value added to the input tensor before applying the logit function. This parameter helps prevent numerical instability when the input values are very close to 0 or 1. The default value is 1E06. Outputs. Output 1 output tensor, a tensor containing the logit values corresponding to the input. Probabilities. The output tensor has the same shape as the input tensor. Steps. Step 1. The torch logit function first adds apes to the input tensor. This ensures numerical stability, especially when the input values are near 0 or 1. Step 2. It then calculates the logit value using the formula logitx log 1x. This transformation converts probabilities x into log odds values, which are unbounded and can take any real value. Challenges and fixes. Challenge 1. Numerical instability when the input probability values are very close to 0 or 1. The logit calculation can become unstable due to division by a very small number. This can lead to none not a number values. Sample use case that resulted in challenge 1. Input tensor 0.00001. 0.99999. Calculating the logit for these values without apes could result in none. Fixes to challenge 1. Using the apes parameter prevents numerical instability by ensuring a small value is added to the input, making the denominator non-zero and avoiding division by 0. Challenge 2. Output range logit values can be unbounded and take any real value. While this is suitable for optimization, it might not be directly interpretable. Sample use case that resulted in challenge 2 for an input probability of 0.5. The logit value would be 0. For values closer to 1, the logit value approaches infinity. And for values closer to 0, it approaches negative infinity. Fixes to challenge 2 to interpret logit values. You can apply the sigmoid function, which is the inverse of logit, to obtain the probability values. This allows you to convert back to a range 0, 1 that is more interpretable. You can also use other techniques like scaling or normalization to make logit values more understandable. Torch, special, logit. Description. The torch, special, logit function computes the logit of a tensor, where the logit is defined as the inverse of the sigmoid function. In other words, it transforms a probability value between 0 and 1 into a log odds representation between negative infinity and positive infinity. This transformation can be helpful in certain machine learning tasks where it's beneficial to work with log odds instead of probabilities. Input a tensor containing values between 0 and 1, representing probabilities. Output a tensor containing the logit of the input tensor. The function calculates the logit of each element in the input tensor by applying the following formula: logit p lop 1p, where p is the probability value. Challenge 1. Input values outside the range 0, 1. Sample use case that resulted in challenge 1 providing input values that are less than 0 or greater than 1. Fixes to challenge 1 ensure that the input tensor contains values within the valid probability range 0 to 1. If the input values are outside this range, they should be appropriately adjusted before applying the torch, special, logit function. Challenge 2. Numerical instability for values close to 0 or 1. Sample use case that resulted in challenge 2 input values very close to 0 or 1 can lead to numerical instability due to the division by 1p in the logit calculation. Fixes to challenge 2 for input values extremely close to 0 or 1. Consider using alternative methods like the torch, special.log1p function for improved numerical stability. This function calculates the log of 1x, which can be used to avoid numerical issues when x is very small. Torch, hypot. Description. This function calculates the hypotenuse of a right-angled triangle using the Pythagorean theorem A, B, C, where A and B are the lengths of the two shorter sides, and C is the hypotenuse. Inputs. Input 1a, a tensor containing the length of one of the shorter sides of the right triangle. It can be any valid p-torch tensor, e.g., scalar, vector, matrix, or higher order tensor. Input 2b, a tensor containing the length of the other shorter side of the right triangle. It should have the same shape as A or be broadcastable to it. Outputs. Output 1a tensor containing the hypotenuse length calculated using the formula SQRTAB for each element pair in the input tensors A and B. The output tensor has the same shape as the broadcasted input tensors. Steps. Step 1. The function squares each element in the input tensors A and B. Step 2. It adds the squared elements of A and B. Step 3. Finally, it calculates the square root of the resulting sum to obtain the hypotenuse length. Challenges and fixes. Challenge 1. NaN not a number output. Sample use case that resulted in challenge 1 input tensors containing NaN values. Fixes to challenge 1. Replace NaN values in input tensors with zeros using torch, natanum before applying the torch, hypot function. Challenge 2. INF infinity output. Sample use case that resulted in challenge 2 input tensors containing INF values. Fixes to challenge 2. Replace INF values in input tensors with a large but finite number using torch, natanum before applying the torch, hypot function. Challenge 3. Overflow. Sample use case that resulted in challenge 3 input tensors containing extremely large values. Fixes to challenge 3. Scale down the input tensors to avoid overflow during calculation. This can be achieved using a suitable scaling factor. YAML. Torch I0. Description. The command torch I0 is not a valid command within the ptorch framework. It is likely a typo or an incorrect command usage. ptorch does not have a built-in command or function named I0. Inputs. Na. Outputs. Na. Steps. Na. Challenges and fixes. Na. Torch. Special. Logit. Description. The logit function is the inverse of the sigmoid function. It takes a value between 0 and 1 and returns a value between -infinity and +infinity. This function is commonly used in machine learning to convert probabilities to logits, which are then used as input to the loss function. Inputs. Input a tensor of any shape containing values between 0 and 1. Outputs. Output a tensor of the same shape as input, containing the logit of each element. Steps. The function calculates the logit of each element in the input tensor using the following formula. Log x log 1x. Challenges and fixes. Challenge 1. The input tensor may contain values outside the range of 0 to 1. Sample use case that resulted in challenge 1. If the input tensor contains values less than 0 or greater than 1, the logit function will return NaN values. Fixes to challenge 1. Clamp the input tensor to the range of 0 to 1 before applying the logit function. Challenge 2. The input tensor may contain values that are very close to 0 or 1. Sample use case that resulted in challenge 2. If the input tensor contains values very close to 0 or 1, the logit function may return very large or very small values, which can lead to numerical instability. Fixes to challenge 2. Use a small value e.g. 1e-6 to prevent division by 0 when calculating the logit. Torch. Hypot. Description. calculates the hypotenuse of the given input tensors element-wise. It returns the square root of the sum of squares of the given input tensors. Inputs. Input 1, a tensor of arbitrary shape containing the first set of values. Input 2, a tensor of the same shape as input 1, containing the second set of values. Outputs. Output 1, a tensor of the same shape as the input tensors, containing the hypotenuse of each element pair. Steps. Step 1, calculate the squares of the elements in each input tensor. Step 2, add the squared elements of the input tensors element-wise. Step 3, calculate the square root of the sum of squares, producing the hypotenuse. Challenges and fixes. Challenge 1, input tensors with different shapes. Sample use case that resulted in challenge 1. Trying to calculate the hypotenuse of two tensors with incompatible dimensions, such as a 2 by 2 tensor and a 3 by 3 tensor. Fixes to challenge 1. Ensure that the input tensors have the same shape or use broadcasting to match their dimensions. Challenge 2, input tensors with different data types. Sample use case that resulted in challenge 2. Calculating the hypotenuse of a tensor containing floating point numbers and another tensor containing integer values. Fixes to challenge 2. Convert the input tensors to a common data type before performing the calculation. Challenge 3, input tensors containing none or infinity values. Sample use case that resulted in challenge 3. Calculating the hypotenuse of tensors containing undefined values or infinities. Fixes to challenge 3. Handle these values carefully, as they can lead to unpredictable results. Consider replacing none or infinite values with appropriate alternatives before calculating the hypotenuse. YAML. Torch I0. Description: the term torch I0 is not a recognized command or function within the PTorch framework. It's likely a typo or an incomplete reference. Please provide more context or clarify the intended use. Inputs outputs steps challenges and fixes torch special Gamma Inc. Description: the torch special Gamma Inc. function computes the lower incomplete gamma function. It calculates the integral from 0 to x of the gamma function. This function is particularly useful in probability and statistics, where it appears in the calculation of cumulative distribution functions for distributions such as the gamma, chi-square, and F distributions. Inputs: a tensor representing the parameter of the incomplete gamma function. This parameter must be greater than 0 and can be either a scalar or a tensor of the same shape as the x input. X, a tensor representing the upper limit of integration of the incomplete gamma function. It can be a scalar or a tensor of the same shape as the input. Outputs: output, a tensor representing the calculated values of the lower incomplete gamma function for the corresponding values of n x. The output has the same shape as the input tensors. Steps: the torch special Gamma Inc. function evaluates the lower incomplete gamma function for each element in the input tensors. It calculates the integral of the gamma function from 0 to the corresponding value of x for each element in n x. Challenges and fixes. Challenge 1: overflow or underflow. Sample use case when calculating the incomplete gamma function for very large or very small values of x or a. The function might encounter numerical overflow or underflow issues. Fixes: consider using alternative functions or libraries that are specifically designed to handle numerical overflows and underflows. Apply appropriate scaling or transformation techniques to the input data to avoid extreme values. Increase the precision of the calculations if possible. Challenge 2. Input validation. Sample use case. If the input values of a are not strictly positive, the function might produce incorrect results or raise an error. Fixes. Ensure that the input values of a are greater than 0 before passing them to the torch, special, gamma inc function. Apply appropriate input validation checks and handle invalid input values gracefully. Challenge 3. Negative values for x. Sample use case. While the lower incomplete gamma function is defined for negative values of x, the torch, special, gamma inc function might produce unexpected or inaccurate results for such cases. Fixes. Avoid passing negative values of x to the torch, special, gamma inc function unless the specific behavior for negative values is well understood and desired. Use alternative methods or formulas that are specifically designed to handle negative values of x. Torch.mul. Description. The torch.mul function performs element-wise multiplication between two tensors. It is a fundamental operation in PTorch, enabling you to scale, combine, and manipulate data within your neural networks and other computations. Inputs. Input 1. The first tensor participating in the multiplication. It can be of any shape and data type. Input 2. The second tensor participating in the multiplication. It must have the same shape as the first tensor, or a shape that is broadcastable with the first tensor. Outputs. Output 1. A new tensor representing the element-wise product of the input tensors. This output tensor inherits the data type of the input tensors. Steps. For each element in the input tensors, torch.mul performs a multiplication operation. The result of each multiplication is placed in the corresponding position within the output tensor. Challenges and fixes. Challenge 1. Input tensors have incompatible shapes that cannot be broadcasted. Sample use case. Attempting to multiply a 2 by 3 tensor with a 3 by 2 tensor. Fixes. Reshape one of the input tensors to match the other, or use a broadcasting operation torch. Broadcast tensors to expand the dimensions of the smaller tensor. Challenge 2. Input tensors have differing data types. Sample use case. Attempting to multiply a tensor of integers with a tensor of floating point numbers. Fixes. Convert one or both input tensors to a common data type before performing the multiplication. You can use functions like torch, float or torch long to achieve this. Challenge 3. Performing multiplication between tensors that have different shapes and are not broadcastable. Sample use case. Multiplying a 2 by 3 tensor with a 3 by 1 tensor. Fixes. Implement the strategy for multiplication that aligns with your desired behavior. For instance, you could use matrix multiplication torch, matmul, if that is more appropriate, or use more explicit indexing and reshaping techniques to achieve the intended outcome. Torch multiply. Description. The torch.mul function in PTorch performs element-wise multiplication between two tensors. This means that it multiplies corresponding elements from the two input tensors, resulting in a new tensor of the same size. Inputs. Input 1. A PTorch tensor representing the first operand in the multiplication. It can be of any valid tensor type and shape. Input 2. A PTorch tensor representing the second operand in the multiplication. Its shape must be either broadcastable or compatible with the shape of input 1. If the shapes are incompatible, PTorch will raise an error. Outputs. Output 1, a new p-torch tensor containing the element-wise product of the input tensors. The output tensor has the same data type as the input tensors. Its shape is determined by the broadcasting rules applied to the input shapes. Steps. Step 1, p-torch checks the shapes of the input tensors. If the shapes are not compatible for element-wise multiplication, e.g., one tensor is a scalar and the other is a vector, it attempts to broadcast them. Broadcasting is a mechanism that expands smaller tensors to match the shape of the larger one, allowing element-wise operations even when the shapes differ. Step 2, p-torch performs element-wise multiplication on the input tensors. This means it multiplies corresponding elements from input 1 and input 2, and stores the result in the output tensor. Challenges and fixes. Challenge 1, shapes incompatible for element-wise multiplication. Sample use case that resulted in challenge 1 trying to multiply a 2 by 2 matrix with a 3 by 3 matrix directly. Fixes to challenge 1 ensure that the shapes of the input tensors are compatible for element-wise multiplication. This can be achieved by reshaping one of the tensors to match the other, using broadcasting rules to automatically expand the smaller tensor to match the shape of a larger one. Challenge 2, data types of input tensors are incompatible. Sample use case that resulted in challenge 2 multiplying a tensor of type float with a tensor of type int. Fixes to challenge 2 ensure that the data types of the input tensors are compatible. This can be done by converting one or both tensors to the same data type before multiplication, using the appropriate function for the desired data type conversion, e.g., torch, float, torch.int, etc. Torch, MVL gamma. Description. The torch, MVL gamma function computes the multivariate log gamma function. This function is commonly used in Bayesian statistics and machine learning for calculating a normalization constant of certain probability distributions, such as the Wishart distribution. Inputs. X, a tensor representing the input values. The shape of X is D, where D is the dimension of the multivariate log gamma function. P, a scalar tensor representing the order of the multivariate log gamma function. Outputs. A tensor representing the multivariate log gamma function evaluated at the input values. The output shape is the same as the input shape. D. Steps. The function calculates the sum of the logarithms of the gamma function applied to each element of x minus the logarithm of the gamma function applied to x, p2. Challenges and fixes. Challenge 1, x must be a positive tensor. Otherwise it will raise a value error. Sample use case that resulted in challenge 1. Torch, MVL gamma torch, tensor -1, 0, 1. Torch, tensor 2. Fixes to challenge 1. Ensure that the input tensor x has all positive elements. Challenge 2, p must be a scalar tensor representing an integer. Otherwise it will raise a value error. Sample use case that resulted in challenge 2. Torch, MVL gamma torch, tensor 1, 2, 3. Torch, tensor 2.5. Fixes to challenge 2. Ensure that the input p is an integer. Torch, Natanum. Description. The torch, Natanum function replaces non-not a number values with 0 and inf infinity values with a finite number. This function is useful for handling numerical instabilities and preventing errors in downstream calculations. Inputs. Input 1, input tensor, the input tensor containing non and or inf values. Input 2, non float. Optional, the value to replace non values with Defaults to 0. Input 3% float. Optional the value to replace positive infinity values with. Defaults to floatinf. Input 4 neginf float. Optional the value to replace negative infinity values with. Defaults to floatinf. Outputs. Output 1 output tensor, a tensor with non-values replaced by non. Positive infinities replaced by posinf. And negative infinities replaced by neginf. Steps. Step 1. Iterate through the input tensor element wise. Step 2. If an element is non, replace it with the specified non-value. Step 3. If an element is positive infinity, replace it with the specified posinf value. Step 4. If an element is negative infinity, replace it with the specified neginf value. Challenges and fixes. Challenge 1. Torch. Natanum might not be able to handle all cases of non or infinity values in a tensor, especially when dealing with complex numbers. Sample use case that resulted in challenge 1 when working with tensors containing complex numbers. Non or infinity values might occur in both the real and imaginary components. Fixes to challenge 1. Use torch, complex to convert complex numbers to a complex tensor and then apply torch, Natanum. Utilize torch, is finite to identify and handle finite and non-finite elements. Challenge 2. Torch. Natanum can only handle scalar values for non, posinf, and neginf. Sample use case that resulted in challenge 2 attempting to use a tensor instead of a scalar value. For non, posinf, or neginf will result in a type error. Fixes to challenge 2. Convert tensors to scalar values using torch, item before passing them to torch, Natanum. Alternatively, use torch, where to selectively replace values based on conditions like torch, isna or torch, isanf. Torch.neg. Description. The torch.neg function is a ptorch operation used to compute the element-wise negation of a tensor. It takes a single input tensor and returns a new tensor where each element is the negative of a corresponding element in the input tensor. In essence, it flips the sign of each element in the input tensor. Inputs. Input 1 a ptorch tensor. The input tensor can be of any data type, e.g., float, integer and dimension. Outputs. Output 1 a ptorch tensor with the same shape and data type as the input tensor, but with each element negated. Steps. Step 1. The function iterates through each element in the input tensor. Step 2. For each element, it performs the negation operation, changing the sign of the element. Step 3. The function assembles the negated elements into a new tensor with the same shape as the input tensor. Challenges and fixes. Challenge 1. Potential numerical overflow. Sample use case that resulted in challenge 1. If the input tensor contains very large positive values, negating them might lead to negative values exceeding the minimum representable value for the data type, resulting in an overflow. Fixes to challenge 1. Ensure that the data type of the input tensor can accommodate the range of values after negation. For example, if the input tensor contains large positive integers, consider using a larger integer data type or converting the tensor to a floating point type to avoid overflow. Challenge 2. Negating a tensor containing none, not a number or INF infinity values. Sample use case that resulted in challenge 2. If the input tensor contains none or INF values, negating these values will still result in none or INF, respectively. Fixes to challenge 2. Be aware that negating none or INF values will still result in none or INF. Handle these values appropriately based on your application's requirements. You might need to replace them with a specific value or raise an error if they are invalid in your context. Torch. Next after. Description. The torch, next after function calculates the next representable floating point number after a given input value in the direction of another input value. Inputs. Input 1 x the input value for which the next representable floating point number will be calculated. This should be a floating point tensor. Input 2 y the direction in which the next representable floating point number should be found. This should also be a floating point tensor. It determines whether the returned value should be greater if y is greater than x or smaller if y is smaller than x. Outputs. Output 1 the next representable floating point number after x in the direction of y. This will be a floating point tensor with the same shape and data type as the input tensor x. Steps. The function first determines whether y is greater or smaller than x. Based on the determined direction, it calculates the next representable floating point number after x in that direction. Challenges and fixes. Challenge 1 the function can be prone to errors if the input value x is already the maximum or minimum representable floating point number for its data type. This can lead to the function returning an incorrect value or producing an error. Sample use case that resulted in challenge 1 calculating the next representable floating point number after the maximum value of a float 32 tensor using a y value greater than x. Fixes to challenge 1 ensure that the input value x is within the representable range of the data type before calling torch. Next after. If the value is at the edge of the representable range, consider using a different approach or handle the edge case explicitly. Challenge 2 the function might produce unexpected results or errors if the input values x and y are too close to each other or if the difference between them is not representable due to the limitations of floating point arithmetic. Sample use case that resulted in challenge 2 calculating the next representable floating point number after a value very close to the maximum representable float 64 value, with a y value slightly greater than x. Fixes to challenge 2 consider the limitations of floating point arithmetic when working with very small differences between x and y. It might be necessary to use alternative methods or adjust the input values to ensure accurate results. Torch. Polygamma. Description. The torch, polygamma function calculates the polygamma function, which is the derivative of the digamma function. The digamma function is the logarithmic derivative of the gamma function. In essence, polygamma x calculates the north derivative of the digamma function evaluated at x. Inputs. N an integer tensor representing the order of the derivative. This is the n in the polygamma x function. X a tensor of real numbers representing the points at which the polygamma function is evaluated. This is the x in the polygamma x function. Outputs. A tensor of the same size as x containing the values of the polygamma function evaluated at each element of x. Steps. The function first calculates the digamma function at each element of x using the torch digamma function. Then, it takes the north derivative of the digamma function using a numerical differentiation method. Finally, it returns a tensor containing the computed values of the polygamma function at the corresponding elements of x. Challenges and fixes. Challenge 1 input values of n less than 0 are not allowed. Sample use case that resulted in challenge 1 torch, polygamma -1. 1.5. Fixes to challenge 1 the input n must be a non-negative integer. Challenge 2 input values of x close to 0 or negative are not allowed. As the digamma function has poles at these points. Sample use case that resulted in challenge 2 torch, polygamma 1. Minus 0.1. Fixes to challenge 2 the input x must be a positive real number. Challenge 3 for large values of n. The numerical differentiation can become unstable and inaccurate. Sample use case that resulted in challenge 3 torch, polygamma 100. 1.5. Fixes to challenge 3 consider using higher precision data types, e.g. double or alternative methods for calculating polygamma for large n. Torch, special, polygamma. Description. The torch, special, polygamma function calculates the polygamma function, which is the derivative of the digamma function. The digamma function is the logarithmic derivative of the gamma function. Inputs: n an integer tensor containing the order of the derivative. X a tensor containing the input values. Outputs: output a tensor containing the values of the polygamma function. Steps: the function takes two inputs n and x. It calculates the north derivative of the digamma function at the input values x. It returns a tensor of the same shape as x containing the polygamma function values. Challenges and fixes. Challenge 1 input values may be negative or 0. Sample use case that resulted in challenge 1 torch, special, polygamma 1. -1. Fixes to challenge 1 the polygamma function is not defined for negative or 0 values. The function will throw an error in these cases. Challenge 2 input order may be negative. Sample use case that resulted in challenge 2 torch, special, polygamma -1. 1. Fixes to challenge 2 the polygamma function is only defined for non-negative orders. The function will throw an error if a negative order is provided. Torch positive. Description: torch positive is a p-torch function that returns a new tensor with all the positive elements from the input tensor. It essentially filters out negative and 0 values, keeping only the elements greater than 0. Inputs: input 1 a p-torch tensor of any data type. Outputs: output 1 a new p-torch tensor containing only the positive elements from the input tensor. The output tensor will have the same data type as the input tensor. Steps: Step 1 the function iterates through each element of the input tensor. Step 2 if an element is greater than 0, it is included in the output tensor. Otherwise, it is discarded. Challenges and fixes. Challenge 1 handling input tensors with negative or 0 values. Sample use case that resulted in challenge 1 an input tensor with values -1, 0, 2, -3, 4. Fixes to challenge 1 the torch positive function automatically handles negative and 0 values by excluding them from the output tensor. Challenge 2 maintaining the shape and data type of the input tensor. Sample use case that resulted in challenge 2 an input tensor with a specific shape and data type. Fixes to challenge 2 the output tensor from torch positive retains the same shape and data type as the input tensor, ensuring compatibility in further operations. Torch.pow. Description. The torch.pow function computes the element-wise power of a tensor. It raises each element of the input tensor to the power specified by the exponent. Inputs. Input 1 input, the input tensor. Can be any type of tensor. Input 2 exponent, the exponent to which each element of the input tensor will be raised. It can be a scalar or a tensor. If a tensor, it must have the same shape as the input tensor. Outputs. Output 1, a new tensor containing the element-wise powers of the input tensor. The output tensor will have the same shape as the input tensor. Steps. Step 1, the function iterates through each element of the input tensor. Step 2, for each element, it raises the element to the power specified by the exponent. Step 3, the resulting values are stored in a new tensor, which is returned as the output. Challenges and fixes. Challenge 1, if the input tensor and the exponent tensor have different shapes, the function will raise a value error. Sample use case that resulted in challenge 1. Python. Import torch, x torch, tensor 1. 2. 3. Y torch, tensor 1. 2. Torch, pow, y. Fixes to challenge 1, ensure that the input tensor and the exponent tensor have the same shape. Challenge 2, if the exponent is a negative number, the function will return a tensor with infinities for elements where the input is 0. Sample use case that resulted in challenge 2. Python. Import torch, x torch, tensor 0. 1. 2. Y torch, tensor -1. Torch, pow, y. Fixes to challenge 2, for negative exponents, it's recommended to check if the input tensor contains 0 elements and handle them accordingly to avoid infinities.